All right, everybody. Full disclosure, you are currently being recorded, right?
So,
Yeah. All right.
are we supposed to sign a waiver?
Usually it just picks up what I say. It doesn't really pick up what you guys say. So I need a better mic. But anyway,
Mike's all
actually they make microphones that are kind of meant to pick up things.
No more fight.
Hi. Listen to his accent.
All right. To get started for this part, of class, you will need something to write with, your calculator, your periodic table, and then the 3 stoichiometry sheets. So the one set of slides, and then the 2 problem sets. One says mole-mole relationships, one says mass-mole relationships. So let's make sure we got those things. And we'll start. What? Yeah. In looking at the calendar for the remainder of this week and into next week will take us through the end of our chemistry unit in physical science. So today we started up with the magnesium oxide lab. We did the first part there. Then I'd like to continue on and do some more stoichiometry problems, review the stuff that we introduced on Tuesday, and then introduce the next type of problem. So we'll get through that next part. And then, like I said before, the last 15 minutes of lab or so, we'll come back and we'll finish up the magnesium oxide lab. You have to take some measurements and clean up. Tomorrow, you will have a short quiz over the stuff that we started Tuesday, that we'll review today, and that we'll introduce today. The real basic stoichiometry principles, right? 2 problems, they're both very short. It's an open note quiz. You can use the stuff that we talked about in class, but I wanted to make sure that we're getting these basic concepts before we build on them and do the more elaborate stuff. Say again?
But they are.
Yeah, they are conversion because all stoichiometry problems are conversion based. After the quiz tomorrow, we'll get into mass problems, which hopefully you'll see by the end of today really shouldn't be all that scary, but it is the next step in the process. Then you guys are off Monday and Tuesday next week. On Wednesday of next week, we will talk about percent healed, and that's really when the lab is all going to come together. So we have to hold on to the lab for a couple of days. We're not quite ready to do all the calculations and answer all the questions just yet. We have to introduce some more concepts, but it was block day, and Then next Thursday we'll devote to review, and then Friday of next week is your test. Okay? Yes, sir.
You know how with there's different types of mole to mole relationships, like it could be 26 to the 23rd. 6 times 10 to the 23rd power equals formula unit.
Yeah, but that's
sort of thing. Does that happen with the?
No. Okay. No. That number is not going to show up much over the next week or so. Test. Oh, I haven't posted objective sheet yet. Hopefully I'll get that done either today or tomorrow. This unit on chemical reactions is pretty long. It started all the way back with balancing equations, so there's a lot of stuff we have to cover there. I'll try and get it up here either tomorrow or Friday, or today or Friday, so that if you guys have some time over your long weekend and you want to start looking at some things, you can do so. Good with the calendar? Okay. Tuesday, we began talking about this idea of stoichiometry. And Hallie, like you said before, stoichiometry deals with our mass and quantity relationships, right? So we're looking at how are the amounts of reactants and products in a reaction related to one another. If we started with this much of a certain reactant, we started with this much of another reactant, how much of this product are we going to end up making? And that's really what stoichiometry is all about. On Tuesday, we introduced the first type of stoichiometry problem, which we refer to as a mole-mole calculation. So I'm going to grab this. I'm not really sure what this happened with my things, but there we go. I'm going to grab this just so we can reference before, or we can reference later. So we talked about on Tuesday that every stoichiometry problem starts the same way. And what's the first thing we have to do if we're doing a stoichiometry problem? It's got to start with a balanced equation. That has to be the first step. and we'll talk about why a little bit more later on. Okay? On Tuesday, I believe, we did an example of a mobile calculation from your slides, right? Okay.
It was,
Let's take a look at,
first stoichiometry.
yeah, first stoichiometry. Let's take a look at the problem set that I gave you for homework on Tuesday nights. Let's go over a couple of those. I believe on Tuesday I gave you the unbalanced equation. Is that correct?
Yeah.
Before you guys left? All right, so let's take a look at number one. So number one says, the combustion of lithium is an explosive reaction that produces lithium oxide. How many moles of lithium oxide form from 2.0 moles of lithium metal? Please go ahead.
Are you going to give us like the unbalanced equations on the test?
Yes, on the test, on the quiz, I will give you the unbalanced equation. It will be your responsibility to balance it, but I will give you the equation. Okay? That's, see, predicting the products when I give you a certain reactant, that's more of an honors kind of thing. That's when, that's when you start getting into that. All right, first, there's the equation as written. Is that equation as written balanced?
Nope.
It is not. I'm assuming that it looks like most of you at least looked at this on Tuesday. Right? So there's our unbalanced equation. Okay? In order to balance it, we have to go here, we have to go here. Okay? Good there? Right. Moving forward, stoichiometry problems, Kelly, as much as you may dislike them, stoichiometry problems are all conversion problems. Right? They deal with conversion factors, they deal with us converting one thing to another. So, conversion factor problems always start the same way, or conversion problems always start the same way. How do conversion problems start? Even before we do time side fraction bar, what do we have to start with, Christina?
Like what they're giving you?
What are we trying to get rid of, right? So in this problem, Christina, right, they're giving us 2 moles of lithium. That's what we're starting with. But what are they asking us for, Christina?
How many moles of
Good. How many moles of lithium oxide? That's what we're trying to get to. This is what we have to work with, right? So in this problem, they gave us some information about one of the reactants of this reaction and want us to predict how much of a product we're going to get. So, Christina, like you said, we start off with what they gave us, and that's 2.0 moles of lithium. Now, Christina, where do we go? Now we go time sign fraction bar. Okay? So, what's going on the bottom of this conversion factor? Okay, moles of lithium have to go on the bottom of this conversion factor because, as we've discussed, conversion factors cancel out the units that we don't want and leave us with the units that we do want. So moles of lithium have to go on the bottom here, right? And then what has to go unit-wise on the top of this conversion factor? Moles of lithium oxide. The fact that this has moles of lithium on the bottom and moles of lithium oxide on the top makes it a special kind of conversion factor. And what did we refer to this conversion factor as on Tuesday? The mole ratio. Okay? Sadie, this is a mole-to-mole problem, but this conversion factor specifically we refer to as the mole ratio. The mole ratio allows us to compare one part of an equation or one part of a reaction to a different part of a reaction. When we set up our mole ratio, units are all taken care of. The next step after we take care of the units is now we have to fill in the numbers. In a mole ratio, where do we get the numbers from? Balanced equation. The coefficients of the balanced equation. So what's the coefficient in front of lithium oxide in this balanced equation? 2. What's the coefficient in front of lithium in this balanced equation? 4. Everyone see where I got those from? Julia, it does simplify to a half. From this point, mathematically, I don't necessarily care how you handled it, but I'm going to write it this way to make the point of the mole ratio, right? That in this case, specifically from the balanced equation, if we start with 4 moles of lithium oxide, or 4 molecules of lithium oxide, remember we said that those kind of are interchangeable, okay? We're going to only end up with 2 moles of, sorry, if we start with 4 moles of lithium, we're going to end up with 2 moles of lithium oxide. So from this point, it's just a math problem. You do whatever you want, how you ever want to do it, and you should end up with 1 mole of lithium oxide.
Number 2.
Is that good there?
Was number 2 right online?
No. Number 2 online is a hot mess.
Yeah.
To be referred to.
Can I do it though?
So here, let's do this, okay? This is how number 2 is supposed to look on your paper.
So just change the hydrogen gas.
Yep. So it says hydrogen peroxide will decompose into water and oxygen gas, where I believe on your sheet it says hydrogen gas and oxygen gas, right? So let's do this, because the one on your sheet is pretty boring. Okay. So here, this is the actual reaction. Okay. It says how many moles of oxygen are formed from the decomposition of 5 moles of hydrogen peroxide. First things first. First things first. Oh, H2O2 decomposes into H2O plus O2. Yeah, the plus signs on the projection turn out looking like minuses. I don't know why. But if you watched it at home, you should get that. So there's your equation. Is it balanced the way that it is? No. First thing we have to do is we have to start with a balanced equation. So let's balance this equation quickly, right? Go ahead, balance it on your own. And there it is. All right. So now, what is this problem asking us for? Okay. How many moles of oxygen? Right? What did they give us to work with? What did they give us to start with? 5 moles of hydrogen peroxide. It also gave you some other information there about a catalyst, right? Do we remember the idea of a catalyst from last week when we talked about reaction rates?
It started the fight.
It started the fight, right? Is it involved in the fight, though? No. Does catalyst show up anywhere in this equation? It does not. This is just some extraneous information that you don't need. Right? Catalyst doesn't go into that reaction at all. That's what a catalyst is or does. So we can just sort of... What? Catalyst? Like, recently? Oh, 8th grade. Okay. All right, so we got our balanced equation. Now, we started off just like any conversion problem, right? 5.0 moles of hydrogen peroxide.
That's like that way to make it.
Yes, it is. Because it's asking you how many moles of oxygen are produced, right? Yeah, we're starting with this much. Next, time sign, fraction bar. Right? What unit has to go on the bottom of this conversion factor? Moles of hydrogen peroxide has to go on the bottom. Then what has to go on the top? Moles of oxygen have to go on the top. Moles of one part of the equation, moles of another part of the equation in the same conversion factor, that makes this what? That makes that our mole ratio for this problem. Okay? Every stoichiometry problem is going to have a mole ratio in it somewhere. It's the gist of stoichiometry. Okay? When we set up our mole ratio, where do we get the numbers from? Coefficients. If there's no coefficient written in front of something, what do we assume that it is? It's a 1. Moles of hydrogen peroxide, it would be a 2. And then that leaves us with 2.5 moles there's no coefficient written, Christina,
Oh,
right?
that's, you get it from the right side?
Yeah, in this case here, Christina, our mole ratio we can use to compare any part of that balanced equation to any other part of that balanced equation.
But on the left side of it, it would be 2 as the coefficient.
Yes, and that's where this 2 came from, right? Because that's the moles of hydrogen. Say again?
Oh, it's not oxygen.
Right. Oxygen has a different coefficient, so it has a different number in mole ratio. All right, we're good there?
How do you explain why the numbers that you use in the fraction, like the coefficients, like how do you know which coefficient to use?
Okay. Well, you're going to use the coefficient that shows up in front of that formula that you're trying to convert from, right? That's how you know which one to use. Like if I'm trying to convert from moles of hydrogen peroxide to moles of oxygen, I have to look at the ratio between hydrogen peroxide and oxygen. The coefficients in the balanced equation tell me the ratio. In order for me to get 1 molecule of oxygen, I need to start with 2 molecules of hydrogen peroxide because the other parts break down into water. The coefficients tell us the ratio between the reactants and the products. So when I'm setting up this conversion factor, the mole ratio, I'm looking at the coefficients for those specific formulas that are involved in the mole ratio. Because that allows me to make a comparison between one part and the other part of that reaction. Okay. Good here? Okay. If you would, let's go back to the slides, the stoichiometry slides.
What's the answer to
Remember,
10?
I believe 3 is 10 if I remember correctly. The answers are posted online. They are correct because I checked them last night after I realized that that was.
Oh, so we're coming up to you?
Yeah, people came up to me yesterday and were like, this doesn't make sense. Like, this is a hot mess. All right. Yesterday, we did an example problem from the front side of the slides. I believe it was the middle one on the bottom row. Is that correct? If you flip it over to the back side of the slides, let's look at the one that's in the top left. It says, second stoichiometry problem.
Oh, that's what we're doing.
Yes, conveniently, this is the same reaction that we did last week in lab and that you did today in lab. So it says, second stoichiometry problem, maximal relationships. When magnesium burns in air, a combustion reaction produces solid magnesium oxide. It says, how many grams of magnesium oxide will you produce from 2.0 moles of magnesium? The order has to stay the same. So what's the first thing we got to have?
Balanced equation.
Balanced equation. Hopefully you've gotten to the point where either you've done this equation enough or you just figured it out, right? Because it's a combustion reaction, we know that these two have to be our reactants. Okay? Then, looking at the periodic table, finding magnesium and looking at how many valence electrons it has, finding oxygen and looking at how many valence electrons it has, there's our formula for magnesium oxide. Is that balanced as written? It is not. Hopefully, you remember how to do it, either because you did it today or because you just turned in a lab report 2 days ago that has this balanced equation on it, or it should at least. Or yesterday, depending on how conscientious you are. How much of a good student you really are.
You know I was going to turn to this on Tuesday, but I couldn't.
Yes, Kevin.
We go over the third mass mole relationship.
We did not, because it was posted online. So, and somebody asked for what the answer was already.
Oh, really?
And I believe I was standing right next to you when I said this answer.
Oh.
7 to 8.
All right, let's go
We're
here.
looking at this paper that has to do with what we're learning today.
All right, let's start this problem up. It's 10, by the way.
I said that. 10 points.
It is 10 points. All right, let's do this problem. Stoichiometry problems, whether you like it or not, are conversion problems. Okay. So if we look at this problem, what are we trying to find here? What's our unknown in this problem?
Grams of magnesium oxide.
Grams of magnesium oxide is our unknown.
So
And then, what are we starting with?
2.0.
We're starting with 2.00 moles of magnesium. So, we start this problem up, 2.00 moles of magnesium. Here's where this problem
Oh, I see.
is different than what we did before. Okay?
Oh. 21.31.
Hold on a second. Let me give my spiel. Okay? So, if we were to do this problem the same way that we did this problem before, what unit has to go on the bottom of this conversion factor? Moles of magnesium has to go on the bottom of this conversion factor. Okay? If we followed the rules for conversion factors that we've done before, we said conversion factors are supposed to get rid of things we don't want and turn them into things you do want. So by following that logic, this would go on the top of that conversion factor. Right? But there's a problem with that. The problem being, well, what is the problem with this conversion factor as written?
It's not moles to moles.
It's not moles to moles. Julia, what do you see about it's mass to moles, but more importantly, it's the mass of this compound to the moles of this element. Is that going to work? No. On Monday, we did problems where we converted mass to moles, but it was always the mass of one thing to moles of that same thing. That we can do by using formula mass and stuff like that. But I cannot convert moles of one thing to grams of something else, at least not in one step. That can't work. This conversion factor doesn't work. Okay? The only time we can have different formulas in the top and the bottom is, Christina, if we compare what? Moles to moles. Right? So, here, we're going to get rid of that on the top, and we can replace it with moles of magnesium oxide. Because this is what? This is a mole ratio, and that's perfectly fine. Just to be consistent, right? Because the mole ratio always gets circled in yellow, just because I started doing that. Yep. Some of you may have noticed that, some of you may not have. But.
Isn't that like the same thing as writing moles of mass?
Yes, but Christina, now, so let's finish this off. Christina, as far as the mole ratio goes, what numbers are going in our mole ratio here?
The bottom is 2.
And?
And top 2.
Okay. So this mole ratio is kind of easy, right? If you have the same numbers on the top and the bottom, how many moles of magnesium oxide do we end up with? Multiplying by 1, right? Now, here's where the problem gets a little different. Is this what this question was asking us for? No. The question asked us for grams of magnesium oxide. And we now have moles of magnesium oxide. But this is what we did on Monday. So another conversion factor.
I need to put that.
What has, units-wise, what has to go on the bottom of this conversion factor? Moles of MgO has to go on the bottom, because that's what conversion factors do. They cancel out the units we don't want. Okay? Then, unit-wise, take care of the units first. What unit goes on the top of this conversion factor? Okay?
Oh, now they're both.
Now they're both the same, right? Now we have mole of one thing to grams of that same thing. This is an acceptable conversion factor.
A second.
Okay? But now, let's talk about this conversion factor. Okay? This conversion factor is like what we did on Monday when we talked about formula mass and converting things for compounds. Okay? Important. Remember this. Okay? When we are doing moles to moles, the mole ratio, we get our numbers from the balanced equation, coefficients of the balanced equation. If we are converting moles of something to grams of something else, what always goes in front of moles there?
A 1.
1. Okay? Even if in the balanced equation it has a different coefficient in front of it. We only use the coefficients when we're converting one part of the equation to another part of the equation. If we're converting moles of something into grams of that same thing, we do it on a 1 mole basis.
Okay.
Because the formula mass, which is what goes here, right, is the mass of 1 mole of that substance, right? So, when we're doing this conversion, 1 goes in front of moles of MgO. What goes on the top of this conversion factor? The molar mass or the formula mass, right? Which is this basically the same thing. But, Hallie, it's not 24.31 for this, right? Because what do you have to do here?
Oh, you got that.
There's both magnesium and oxygen in this formula, right? Add them together.
Ah.
And you should end up with 40.31. So, Kartik, same idea as molar mass, right? But just make sure that we take into account all of those things that are in there. Okay? Now we run this through, and you end up with 80.62. Sig dig wise, that gets us 80.6 grams of MgO.
You would put 6 0.
Nope, because that's 4 sig digs, right?
One and 4 sig digs, we just keep it 6 2.
Say again?
Keep 1 and 4 sig digs, we 6 6.
Right, yeah.
And you have to do it because.
Yeah, because we're still working off the significant digits of the original number in the problem, which was 2.00 moles.
I get it.
Okay, is that good? All right, let's flip to the worksheet that I gave you, or the problem set that I gave you today that says mass-mole relationships up at the top.
5.
There are 5 of them. Let's take a look first at number 3. Let's take a look first at number 3.
Cool
Coal gasification.
That's original.
So it says coal can be converted into methane gas by a process called coal gasification. And it gives you the equation. It says how many grams of carbon are needed to react with water to produce 1 mole of methane. Stoichiometry problems all start the same way, right? What do we have to start with? Balanced equation. That equation as written is not balanced. Balance it. We talked about the idea that when we're balancing equations, it's a good idea just to look at things that only appear in one formula on each side. So in this problem, don't start with trying to balance coal or the carbon. Right? Start with hydrogen. That's probably the easiest one. So there's our balanced equation. Now, this problem is a little bit different because, not real different, just a little bit different. What are they asking us for in this problem? Okay, how many grams of carbon are needed, right, to produce 1 mole of methane? So in this problem here, Christina, just going back to something we kind of talked about before, in this problem, they're giving us information about one of the products, right? We know that out of this reaction, we need to produce 1 mole of methane for whatever reason it might be. So now we're going to work backwards and say, okay, if we know we have to end up with 1 mole of methane, what do I have to start with to get there? Does that make sense? In the other problems, it basically gave you something about the reactants. But yeah, in this problem, right, the one we just did, it gave you information about one of the reactants, right? It said we start with 2 moles of magnesium. How many moles of magnesium oxide do we end up producing? In this problem, right, in this problem, they're basically giving us the end. And we're saying, okay, I want to end up with 1 mole of methane. What do I have to start with to get there? Does that make sense? It doesn't change how we do the problem. It's just a little bit different way of looking at it. So, if it doesn't change how we do the problem, how does this problem start? That's methane. All right. Time sign, fraction bar, right? What unit has to go on the bottom of this conversion factor? Moles of methane has to go on the bottom of this one because it's got to cancel. Okay? This problem is asking us for grams of carbon, but can we put grams of carbon on the top of that conversion factor? We cannot. But we can compare moles of methane to moles of carbon, right? Moles of methane on the bottom, moles of carbon on the top. That makes this conversion factor what? This makes this conversion factor our mole ratio. Mole ratio.
Sorry.
Okay.
Why do you need a mole again?
We can only compare different parts of the same equation through the mole ratio.
The same thing.
Right. Well, we can only compare different parts of an equation through the mole ratio because we know proportionally if we have numbers of moles, it's the same number of things. Okay? That's the only way we can compare one part of the reaction to the other part. Remember, Hallie, we said that the mole ratio, the coefficients, give us the ratio between this part and that part. And that's only what the mole ratio does for us. Okay? So from our balanced equation, 2 here, 1 here, right? Does that make sense where I got those numbers from? We work that out. We end up with 2.00 moles of carbon. But what did this problem ask us for? Grams of carbon. Times sign, fraction bar, right? Moles of carbon has to go on the bottom of this conversion factor. It's got to cancel. But now, we can do that, right? We can put moles of carbon at the bottom and grams of carbon on the top. Right? When we're converting moles of one thing to grams of that same thing, what number goes in front of moles? 1. Not the coefficient from the balanced equation. And then in this case, what number are we putting in front of grams? 12.01. Now, Hallie, in this case, we just get the average atomic mass because there is no compound here, right? It's just an element.
Wait, what's 12.01? Wait, that's
the atomic mass. It's the average atomic mass of carbon because, Christina, in this case, right, we only have a single element. It's not a compound that we're trying to find the mass of. Right?
so it'll be 24.
So when you work that out, 24.02, 3 sig digs give you 24.0 grams of carbon. Are we seeing how it's fitting together? Okay. So two things before we finish up with the lab. Okay. First, problem number 4 on this problem set. Okay. Just real quick. I'm not going to walk through it with you because we don't have quite enough time to do that. But when we see here, it says this problem is asking us how many moles of NO are formed. But it says you start with 824 grams, right? So in this problem, what's the first thing you're going to have to do?
You have to do it backwards.
You have to do it backwards. Can we compare grams of one thing to moles of something else? No, but we can convert this grams number into moles, then go moles to moles. Same idea, right? We just, like you said, Josh, we just do the conversion from grams to moles first. Okay? Is that good for number 4? So here, See, in this problem, like I said, it starts with 824 grams of ammonia, right? That's what it says for number 4.
Oh, so you just do the second one first?
Yeah, you got to do the conversion to convert grams into moles first, then compare moles to moles. Okay. The last thing on numbers 1 and 2. On numbers 1 and 2, I did not give you the equation, so I will put them up here for you now. So if you would like to look at the equations for number 1 and 2. Okay. This is the equation for number 1 up at the top. Say again. Oh, here, let me do this. Come on. Or not. This is where it did not. Oh. So, for number 1. C6H12O6. That's glucose. Plus O2 gives you CO2 plus H2O. Because it's a combustion of a hydrocarbon. Then for number 2, CNO, zinc oxide, plus carbon gives you zinc, Tn by itself, plus CO2. Answers to this problem set are posted on Thursday's date on the calendar. So it says mass mole problem set 1, 2, 5. We didn't get to 3 and 4, so if you want to do all of them, you can. Answers to all of the problems are posted there on Thursday. Tomorrow, you will have a quiz over the mole, and the mass mole, so the problems that we did today, basically. Okay.